For the last many decades, we've been exploring and understanding quantum mechanics at many different scales. And recently, we've been getting the capability to harness quantum mechanics to control systems, to understand quantum phenomena in deeper ways. And we're starting to realize that there's ways to use quantum mechanics to do things that you couldn't do another way. The Center for Quantum Leaps is an interdisciplinary center, and the purpose of the center is to connect those working in quantum technologies to the scientific questions that different researchers are pursuing at Washington University. And the goal is to find areas where quantum advantages, quantum technologies can really help drive advances forward in different research fields. Our center really focuses on developing those quantum technologies, expanding our understanding of quantum technologies, but also finding new places where those technologies can have impact. At WashU, we have the advantage of being a highly interdisciplinary campus. We have strong connections between physics, which is really focused on fundamental questions in physics and quantum technologies, but also with chemistry and material science and engineering, and even the medical school. So there's a breadth of research foci. And it's in those communications, the collaboration between my research in physics and maybe my colleague in the medical school, that we hope to find questions that can be tackled in a better way, a new unique way with quantum technologies.
We've created this center to really see what we can do with quantum sensing. What can we use this for in material science? What can we use this for in biology? For drug discovery, one of the things we want to do is to measure temperature rises as we put drugs on a cell. This will tell us something about which drugs affect the metabolism of the cell. Quantum opens up a whole new way that we can very sensitively measure specific molecules inside the cell. Quantum sensing is something that's really new. It's taking advantage of long understood quantum properties, but now having those in a way that you can encapsulate and perhaps put inside of a living cell and watch how different molecules are affecting that quantum sensor. So you really need an expert in the cells that you're studying. You need an expert in the quantum microscope. You need an expert in the drug discovery. And the center is really bringing these people together. Science is getting more and more complicated, more and more collaborative. And so the Center for Quantum Leaps is playing the absolute central role in being able to do this and jumpstart these kind of really exciting new projects.
And the Center for Quantum Leaps gives us the space to collaborate across physics, chemistry, medicine, all of the different areas at WashU. And so it's a good opportunity to be able to talk to people that are working in a similar field but from a different perspective. And there's a surprising amount of expertise on campus in open quantum systems, both in terms of hardware, in terms of theoretical background, as well as in terms of potential applications. For problems in quantum chemistry, or if you go further into biology and other systems where you have really large complexes involved in any type of reaction, it's exponentially hard to solve these problems in any form. And so quantum computing offers a platform to potentially reduce the scaling of these problems and give us alternative ways of looking at these types of problems that we just can't really solve classically, and we've been trying to approximate for many years, and quantum computation will just give us a different perspective on how we could potentially solve these problems.
To me, WashU is a very, very special place where we can actually have all different kind of expertises from all different fields that come together and really explore the power of quantum mechanics and quantum technology. The research I'm working on here is mainly focused on using solid-state spin defects in diamond and other type of solid-state materials to realize quantum-enabled sensing tasks that is beyond the capability of any classical spectroscopy methods, and also to perform quantum simulation tasks that is impossible for classical computers to perform. The goal from my perspective is we're hoping really to advertise this spin defects or spin sensors in diamond as a very, very powerful and all-in-one sensor to all different applications or all different broad other fields, including material science, medical study, biophysics, and also earth and planetary science. We really hope to use this to achieve all different kind of goals that cannot be achieved using current technologies.
Here, what we're thinking about is quantum information, quantum computing, and we've talked about quantum sensing here at Washington University. These areas are ways where we can enhance scientific discoveries by using and harnessing the special properties of quantum mechanics to do things that we hadn't even envisioned a decade or two ago. So let's think about drug development for a moment. Really, this is a tremendously difficult process, but if we could compute what a molecule would look like that would help create that cure, create that drug, that would be tremendous. But you need incredible computing power to predict what that molecule might look like that would bind at a target. And to do that kind of computation is incredibly difficult. So we need something with a lot of processors, a lot of bits that can do that kind of computation. And right now, the way that binary computers work in their ones and zeros, that is limiting us, whereas quantum computation and quantum mechanical routes, thinking through how those might be deployed, means that we could do much, much, much larger calculations. The NRT grant is from the National Science Foundation, and NRT stands for NSF Research Traineeship. And this is a way to enhance graduate education and training. They give us money to try new models for graduate education. Here the focus is on quantum sciences and engineering. And so the initiative that we're spearheading has to do with workforce development, but also professional training that considers pathways outside of the academy, specifically in the quantum sciences area.
We envision a center that really pursues the forefront of quantum materials, that advances quantum sensing, that utilizes these quantum technologies really to advance problems beyond just the physical domain of chemistry, materials, and engineering, but into the life sciences and biomedical sciences. Quantum technologies and the quantum leap is real and will really drive innovation in the future.